Elastic collisions occur when you have two objects that collide, and in the interaction, you're actually storing the energy in compressed bonds. So this goes back to our ball and spring model of solids, and you can think of rubber balls are a really good example here, that they can flex and are basically like little springs storing the energy, and then they push each other apart, and they've converted the potential energy of the deformation of the compression into kinetic energy. So we have kinetic energy, we have some sort of interaction, and then at the end we again have kinetic energy. And the idea being here that your kinetic energy is conserved. So the signature of an elastic collision is that kinetic energy is completely conserved, and we don't have to worry about the exact interaction in between. So the equations that we use here are a little bit complicated. They are in the equation sheet, and the most important thing to know about them is that one, you have to use the correct notation and actually get your variables right, and two, it's only true if ball 2 is initially at rest. So we have to figure out what we're going to do if ball 2 is not initially at rest. So the first thing to notice is that these equations are in terms of the mass of ball 1, the mass of ball 2, the initial velocity of ball 1, and then we have two different equations for calculating the final velocity of ball 1 and the final velocity of ball 2. The book goes through the derivation of these, which I'm not going to go through, but there's two ingredients. One is conservation of momentum, the other is conservation of energy. So this is really just deriving it, giving you the final thing you can plug values into, but if you wanted to, you could rederive them yourself, that you have the skills necessary to do that. There's nothing that tricky here. What's important to notice is that the initial velocity of ball 2 doesn't appear in these equations, and that's because we said it's initially at rest. The derivation of these equations have used this, so if this is not true, you can't use this. The other thing to note is that because it depends on both mass 1 and 2 and that it's not symmetric, you need to make sure that you've correctly identified ball 2 as the one initially at rest. Otherwise, you're going to get the wrong velocities. So note that it does matter which one is 1 and which one is 2 in these equations. So we can also look at some special cases based on the relationship between masses 1 and 2. And you can look at this if you plug values into those equations or do approximations. But one situation is where the masses are equal. Ball 2's at rest. Ball 1 comes in, hits ball 2, and ball 1 is now at rest, and ball 2 is going forwards with the same initial speed. So this is one option that can happen, and again, if you plug values into the equation, you'll get that. A second case is when ball 2 is really, really small, the mass of it, compared to ball 1. Now, in this approximation, ball 1, it says, hardly slows down. Now, it isn't identical, but we're doing an approximation here. Ball 2 is then knocked forward with twice the speed. Now, it's a little hard to see that at first, but I can come back to it a little bit later. The final case, case C, is when mass 1 is much, much smaller. So mass 1 is the one moving, ball 2 is at rest, and basically mass 1 just bounces off ball 2. Ball 2 barely moves, and so because of that, we would say ball 1 barely has any loss of speed. So these are probably the two that are a little easier to see why that might happen. If you think of mass 1 being really small and mass 2 being really big, that's like this almost being a wall. And in this case, if they're equal masses, this is the only way that energy and momentum can be conserved, and hopefully that's more obvious. So you can get these by plugging it in. This case, we have to understand something about frame shifts to see why this would be true, but it's actually a similar scenario to this one if we shift the frame. So why do we need to shift the frame? The equation that has been derived for you is only true if ball 2 is at rest. So what do you do if ball 2 is moving? Well, this goes back to that idea of reference frames. We can shift into a reference frame where ball 2 is at rest. So let's talk through this. Initially, we have a scenario where we have a person, standing on the ground. We can call this the lab frame, but we have our scientist who is on the ground. The scientist says that ball 1 is moving to the right at 2 meters per second, and that ball 2 is moving to the left at 3 meters per second. The scientist says, well, crap, I don't know how to calculate what happens next because I don't actually know how to plug these values into the equation because I know the equation is not true. Well, what I can do is put the scientist instead on ball 2. So this is now a different scenario. Now, if we have our scientist who's actually on ball 2, that scientist says that ball 2 is at rest. Now the scientist knows how to plug these values into the equation. But ball 1 now has a different velocity. And so this is where we would actually say, what am I trying to do? Well, how do I do this reference frame shift? I am adding my 3 meters per second to each velocity, right? So you can go back, we did this, I think in chapter 4. And so we added 3 meters per second to each of these, which got us to 0 in ball 2, but gets us from 2 meters per second to 5 meters per second for ball 1. So this is an equivalent scenario, but it's in a different reference frame. Now you can plug the values into the equation. But be careful, after you plug these values into the equation and you get your final velocities, you then need to shift it back to the lab reference frame. If you were asked about the scenario in the lab reference frame, you actually need to provide your answers in that reference frame. So do be careful about that. So now let's go back to case B. Now, let's do something kind of crazy here. Let's look at this scenario and actually shift reference frames and renumber our balls. So first I say that ball 1 is actually the small one and ball 2 is the big one. That means that I need to make ball 2 be at rest. I shift both of the velocities of both ball 1 and 2 before and after, and so if I shift it so that ball 2 is at rest, that means that actually, because the velocity was the same, it's at rest both the before and after situation. Ball 1 is initially moving to the left, but then it's moving to the right, but less so. All I have literally done now is recreated case C. So case B before was actually different, but once you switch the index of the two balls and do the reference frame shift, it actually looks the same as case C. So that might not make a lot of sense, but that's one way that you can see that this is the answer. So for this simplification, one way to see that it makes sense is to plug values into the equations, but a different way to see that it makes sense is just switch the indices, which is completely allowed, do the reference frame shift, and then you're just to case C. So what is our overall tactic when analyzing elastic collisions? So first, you must have ball 2 be at rest if you just want to use the equations that have already been provided to you. You can always rederive them if you want to deal with a different situation, but it's going to be a lot of algebra. So what's recommended is you use the Galilean transformations, you transform to a different reference frame where ball 2 is at rest. Then you get to plug stuff into the elastic equations now that ball 2 is at rest. And then after you get your final velocities, you transform back into the lab frame. So part of the reason we covered reference frame shifts at all is because we do sometimes need them here. It is going to be simpler than actually calculating out conservation of energy in a general case, even though that is an option for you as well.